All right. Thank you very much. I'm really pleased to be here. This is pretty exciting for me. And actually, I was planning to get rid of an article of clothing too, but I can't do this. I don't get to do things like this too often. I think this is kind of a first for me. So it's sort of like the first kiss. I'll probably remember this for the rest of my life. I'm also very pleased for the first time in my career to be the warm-up act of pornography. What I really want to tell you about, though, is this incredible world and the amazing mission, amazing journey that we've had in discovering it. This is an image mosaic of Titan, a collection of images that we've taken from a spacecraft called Cassini that I'll tell you a little bit about. You see the title of my talk there is The World Strange and Familiar. And if nothing else, I want you to remember tonight that this place really is, at once, extremely foreign and strange to us, but also familiar in many, many ways. We travel across the solar system and find a place that's so incredibly familiar. As Jamie mentioned, Saturn is a satellite, an icy satellite that orbits Saturn all the way out in the solar system, in the outer part of the solar system. So we're in here in the middle, and Saturn's down here 10 times further from the Sun, and it has satellites orbiting it. Titan was discovered by this Dutch guy named Huygens in 1655. I think Huygens was getting jealous of Galileo. I'm sure you guys have heard of Galileo, who discovered his satellites around Jupiter, the 4 Galilean satellites. And then Huygens sort of got jealous, and the scientists do it. He wanted to build a bigger telescope than Galileo had, and he did, and then he found Titan. So that was his reward. This is what Titan looks like from a picture from the Hubble Space Telescope. And besides, I think, the sort of aesthetic aspect of Titan casting its shadow on Saturn here, I think this picture actually tells a lot about what I'm going to say, and that is until recently, we didn't know very much about Titan. All we could see is these thick haze that cover Titan and that make it appear orange in this picture. So not being able to penetrate through the clouds, we sent a spacecraft there, and this is where the story really begins. This is the spectacular night launch in 1997, for those of you who remember when pictures used to do this. This is the spectacular night launch by an amateur photographer on Cape Canaveral of the Cassini spacecraft. And Cassini was headed towards this place where all we really knew was that it was covered by these orange hazes that we couldn't see through. So people went in the lab and did test tube experiments like the one you see on the right. I think this is the basement of my alma mater, Cornell, where people were putting together organic material with nitrogen and then radiating it to see what kind of soup they could make and whether life could ever arise in this kind of world. But the spacecraft went out there. It went through this incredible trajectory. I was actually just doing a radio interview with this reporter who didn't believe that you actually do an Earth flyby, a Venus flyby, a Jupiter flyby before you get out to the outer solar system. So you use all these other planets like a slingshot to swing the spacecraft around and accelerate it towards Saturn. A few years later, in 2004, we finally got there, and I think we discovered a place that puts Titan together with some of these other worlds that are a little bit more familiar to us. Certainly this one, but also Mars and Venus, places that have active processes acting on their surfaces, things changing with time, weather, climate, liquids. I think Titan really fits in that family of objects in the solar system, and not like many of the other outer solar system bodies that are just icy and cold and dead. And I'll tell you more about this. So this is what the spacecraft looks like. It's actually pretty big as spacecrafts go, and you see it had a component called Huygens. You've already heard of Huygens, that actually separated from the spacecraft and landed on Titan. Jamie already mentioned that one of the things that the spacecraft found was that Titan might actually have liquid on its inside. And the way that was found is that very much like you test whether an egg is hard-boiled or soft-boiled. Does anybody know? Yeah, you spin it, and hard-boiled egg spins differently than soft-boiled egg. And the reason is that a soft-boiled egg, here we go, thank you. A soft-boiled egg, the inside spins independently of the outside, so the hard part spins and then the soft part catches up to it, and then the way I do it is actually stop the egg and then it keeps the inside keeps going and it starts spinning again. So the same thing people did with the spacecraft observing Titan, they could look the way Titan spins very, very accurately by comparing two pictures that the spacecraft took when it flew by, and they noticed that the planet isn't spinning quite right compared to a solid body. So they figured out that it must be squishy on the inside. There's a lot of debate. No, seriously, there's a lot of debate about how thick, if at all, this ocean is. Titan also exhibits landforms that are strangely familiar to our own. I was just in the Sahara a few months ago looking at sand dunes. These are sand dunes taken from the radar instrument on Titan. You see, they look very much like terrestrial sand dunes. They are diverted by mountains here. They have triple junctions, the same way sand dunes on Earth do. Here's a picture of similar scale sand dunes, both the height and the distances between them taken from an astronaut on board the shuttle. And again, you see these are sort of a couple of kilometers apart, maybe a few hundred feet high. Here is another picture from Titan. This one is a bunch of channels that are all draining into a basin on Titan. And they too exhibit a lot of the familiar things that terrestrial geologists might recognize, like meandering river forms, places where the river turns, and places where the river splits apart and merges again in contributing networks. And here is a picture that a friend of mine took on a flight from Tucson to LA, like he often does. He looked out the airplane and saw these channels, and he said, hey, I've seen something just like that recently from spacecraft. And you see again the same form, same sort of scale that the channels take, the meandering nature, the braided networks. This is kind of a sciencey chart, but I actually want you to understand this because it matters. The reason why I show it is because what you see here is a temperature pressure profile of the Earth's atmosphere. Some of you know that the Earth's atmosphere gets colder as you go higher up, then it actually gets warmer again, so there are temperature inversions in the atmosphere, and there are different layers where clouds form. So this is the troposphere where we live, stratosphere where airplanes fly, and so on. Titan actually has the same thing, except the whole thing is colder. So Titan's atmosphere also has inversions, also has clouds, also has these hazes that I talked about. But there's something fundamentally important here, and this is what I want you to pay attention to. Much of our existence here on Earth we owe to a fact that's summarized on this chart. The fact is that the temperature near the surface of the Earth is right around 0 Celsius, or 273 Kelvin here on this chart. So that means that water on Earth has the opportunity to evaporate, reprecipitate, rain down, and form a hydrologic cycle that drives much of what we see around us, and I think is the reason why we can exist here. Titan is 200 degrees colder than Earth because it's 10 times further from the sun, so it gets a lot less sunlight, 100 times less sunlight. But there is a substance in Titan's atmosphere that is also capable of doing all these things that water can do. It's near its triple point, so it can evaporate, recondense, and rain down, and that substance is methane. On Earth, methane is very volatile, so it just evaporates and stays in gas form unless you go to very cold temperatures and high pressures. But in Titan's temperature and pressure, methane can be liquid or gas. So methane acts like water in Titan's atmosphere, and water is as hard as ice. It is as hard as rock on Titan's surface. So the ice on Titan is like the rock on Earth, and the methane on Titan is like the water on Earth. And these channels that you saw were actually methane channels carving into water ice, unlike the water channels here on Earth. So here's the spacecraft getting to Titan. You see that the Huygens is going to separate from this spacecraft. It's going to have a little bit of a spin to it, so it stays stable the same way that a bicycle is stable when the wheels are spinning. The spacecraft pushed the Huygens probe away from it, and then Huygens entered Titan's atmosphere at very rapid speed because it was accelerated by Titan's gravity. So it needed to have a heat shield protected from the intense heating of this supersonic speeds when it entered the atmosphere. This shield also slowed it down on the way in. Titan's atmosphere is about 1.5 times thicker than Earth's, which is actually quite similar to us planetary scientists. A sequence of parachutes had to open. This all has to be done in remote control because light takes many minutes to travel from Earth to Titan. So the spacecraft has to be totally autonomous. The sequence of parachutes has to open, each one of a different size, because the parachute was large enough to slow down the spacecraft upper parts of the atmosphere is way too big near the lower part of the atmosphere. And then the third parachute opens, the spacecraft sort of comes down, the radar acquires the surface so it can release the last parachute just at the right moment, and then the spacecraft comes to rest on the surface sort of at this speed here. So this was really exciting, and you can imagine all us geeky scientists being glued to our computers when this was all happening. There was a big press conference to announce the results of what had happened. Everybody wanted to know, what are we going to land in? Okay, we had never seen the surface before, and there were a great many questions about what the surface of Titan was going to be made out of. Is it going to have liquid methane? Because we knew that there was methane there, and we knew that it could be liquid. Is it going to be a big ocean, the way Carl Sagan, those of you who have seen Cosmos, hypothesized? Is it going to be land? What's it going to be? And in fact, this was the whiteboard in the kitchen where I worked over at Saturn. You see, we were all taking bets about where we were going to land in. A bunch of people thought we were going to land in water. Some of the students thought we were going to land in tar. These organic molecules grow and have a longer chain in Titan's atmosphere and then fall down eventually when they're big enough, making basically these tarry substances sort of what we put on the roof. One student thought he would actually land in liquid in a lake or an ocean. A bunch of people thought we would never know what we landed in. We would be able to see it, but we won't know what it's made out of. My student shares my skepticism. He thought he would be dead on arrival. And a very famous Caltech professor thought he would be eaten. I'm not making this up. This is actually what we ended up landing in. You see on the right, this is an amazing success, the first image from the surface of Titan. And you see a landscape that's actually quite familiar to our own again, strangely familiar. A bunch of boulders strewn on the surface. They're rounded off. They look like they've rolled in something on the way down. They actually rolled in this valley network that you see here. So these are pictures that were taken from the spacecraft as it was coming down to the surface. So they rolled down and were delivered to this basin. The spacecraft landed over here relative to this picture, and these boulders probably rolled down in this fluvial system. Something very familiar to what we might see on Earth in an environment that's completely different, where ice is hard as rock and the chemistry is all different. Here's a picture of a lake on Titan. This one's called Lake Ontario. It's about the same size as the one that you are thinking of. And much of my research and my students' research actually focuses on this lake. We see examples of shorelines around this lake that are bounded by mountains. There's an erosional form here, very much like the shorelines around LA that are carved by wave action. And then as we come around to the other side of the lake, you're going to see that there's actually a river that empties into the lake and dumps its sediment into it. So for those of you who know, what is it called when a river dumps its sediment into a lake? This has been in the news a lot. Delta, right? So like the Mississippi River Delta is where all the sediment that's carried by the Mississippi keeps filling up the ocean basin and forcing the water places where we don't want it to go. And here is at Delta on Titan, there is the river, and there is the sediment that was delivered to this lake. So we travel across the solar system, and we see landforms that are so familiar to our own. I actually spent the last couple of days trying to decide where to land the next Mars rover, and I'm really hoping that we go to a delta on Mars, a place called Ebeswald Crater, because they're such a good place to preserve organic material that may be the precursors for life. Here's a very aesthetic picture that was in the press. Here we see something that we've looked for a long time, the specular reflection of light off of Titan's lake in the northern hemisphere. If you ever fly over the ocean, you see the same thing. There's always a point in the ocean where the sunlight reflects straight into the airplane. And here is a picture that the spacecraft took the same way. So I hope you're getting a picture of a world that is dynamic, that has methane, that is evaporating and raining back down, it has seasons, it even has longer climate cycles, very similar to terrestrial, to our own Milankovitch glacial cycles. So it's a very dynamic world that in many ways mirrors our own, even though it is so strange in its temperature and chemistry. I want to take the last minute to talk about something that serious scientists normally don't talk about, and that is life in the universe. I think it's actually quite important to talk about life and the search for life in the universe, especially to the general public, because in many ways this motivates, at least intellectually, it's not every day what I get up in the morning and do, it motivates intellectually sending spacecraft and spending taxpayers' money on exploring the solar system. So I think a lot of people really want to know, what is it that we're trying to do? I'm going to frame the discussion in terms of the only equation I'm going to show in this talk, and it's not a real equation, okay, so don't worry about it. I mean, I'm going to explain it, but you'll see that it's really a framework to discuss what it is that we mean in the search for life in the universe. So the equation is quite famous. It's called the Drake equation, after a famous guy named Equation. And he said that, what Drake said is that the number of aliens that we expect to find in the solar system is proportional to all these factors. Okay, so this is how many aliens we expect are going to make contact with us Earthlings. And it's a bunch of factors. The first factor has to do with the rate at which stars form. So we want to figure out how many places in the universe can make contact with us. So we need to know how many stars form. That's the rate of star formation, R. And then we need to know, of those stars, how many have planets? That's the fraction of stars that have planets, that's P. So actually people are making progress on these questions. Astronomers are making progress on these questions because they use telescopes to look deep into the galaxy and see how many stars are forming every year. And they also find planets around stars nowadays, which also tells you how frequent this phenomenon of planets is. So we're making progress here by using big telescopes like the one in Hawaii and the one that's now in orbit called Kepler. The next factors have to do with how many of these stars that have planets are habitable. How many are Earth-like? That's NE. And then of those that are Earth-like, how many have life on them? And of those that actually were able to develop life, how many of those life forms develop intelligence? You might argue we still have yet to observe that. Of those that are intelligent, how many develop communication capability so that they could make contact with us? And of those that could communicate with us, how many survived long enough to do so? So that's the lifetime of these planets. So there are several factors here that are not really, I think, purely scientific questions. They're quite interesting. It's not what I'm interested in studying, but the fraction of life forms that are intelligent, the fraction of those intelligent life forms that can communicate, and how long they live before they develop communication capabilities versus developing weapons that are large enough to destroy themselves. I think these are really sociological questions as much as scientific ones. But nonetheless, I think they're worth thinking about because ultimately that's what will determine whether we have a chance of finding aliens or not. What I think Titan is special, the reason why I think Titan is special is because of these two factors here, the number of planets that are Earth-like and the number of Earth-like planets that actually develop life. And I think it's really quite important to understand this because this is why we spent a couple of $1 billion and sent spacecraft there. I think what Titan is forcing us to think about is what is the definition of Earth-like? So we go around the solar system and we look at other planets around other stars and we say we're looking for environments that are Earth-like. Those of you who pay attention to the news might hear that there's a big search going on of who's going to find the first Earth-like planet in outside our solar system. But I think what I'm hoping I showed you is that we really have to think about what is the definition of Earth-like. We go to a place that's 10 times further from the sun. So if we found this place around any other star, everybody would say, no way, this place is too cold, it would never have life on it. But we go there and we see active hydrology made of methane. We see climate cycles. We see organics. We see a place that's very much alive and that's reminiscent of our own world. So I think the first thing we have to ask ourselves, are we too ethnocentric or geonormative? Those of you know what that is. And our definition of what Earth-like is might be way too narrow, just based on our own biases. And the second thing is this factor, the fraction of planets that are Earth-like that have life on them. Okay, this is really important. So today I spent the day driving a rover on Mars, and everybody wants to go find life on Mars. Mars is very much Earth-like, and it's close to the Earth, so it's easy to reach. But actually, I have to say that finding life on Mars is kind of a complicated question. Because even if we found evidence of life on Mars, it's still not quite good enough for me. And the reason is that we can show, and people have shown, that there are trajectories from Mars to Earth where rocks can carry bacteria to Earth and not be very strongly heated. Bacteria can make it from Mars to Earth and presumably the other way without killing off all the bacteria that live on the rock. And these things happen. Big impacts hit Mars, and rocks get ejected. So it's possible that if we find life on Mars, it was actually originated from Earth, or as one of my colleagues at Yale Tech thinks, that actually all of life on Earth originated on Mars. And if we just find life on Mars that originated on Earth, that's not quite good enough.